We should start. So the next talk is by Sergei Avdonin, one of the organizers from the University of Alaska Fairbanks. The talk is Inverse Problems for the Schrödinger Operator on Metric Graphs. Please start, Sergei.
Thank you, Ricardo, very much for introducing me. I will talk about inverse problems on metric graphs, and so I do not need, because of talks of Professor Yurko and Professor Kravchenko, so I can skip some my explanations. And so metric graphs are just graphs where all edges identified with intervals of real lines with standard Euclidean metrics. And by gamma, I will denote vertices of degree 1. And quantum graphs are metric graphs with differential equations with some coupling conditions or matching conditions. And there are many applications now of so-called differential equations networks or differential equations on metric graphs, including quantum physics and many other more standard applications in engineering, geophysics, and so on. And I start with definition of spectral and dynamical inverse problems on interval, then briefly describe the boundary control method, and then discuss inverse problems first on trees without graphs, without cycles, and then discuss inverse problems on general metric graphs. And I will use connections between control and inverse problems, and between spectral and dynamical approaches, because in our investigations, these connections are important, and technically and mostly methodologically. And I will try to answer some questions of Vyacheslav, which he and remarks from his yesterday's talks and today's questions. This is, in my opinion, some simple misunderstanding. Okay, first of all, standard inverse problems for Sturm-Liouville problem, because it is already discussed. I will not described it in detail. So there are several classical statements of inverse problems. So inverse data may be spectral data such and spectrum and traces of, say, derivative eigenfunctions. So for definiteness, I will consider the Dirichlet boundary conditions on graphs and the intervals. So and consider traces of derivatives of eigenfunctions as a part of spectral data. Another classical statement is inverse data. It is Weyl function. But now I briefly described dynamical inverse problems. So dynamical inverse problems are important themselves because they, independently of spectral problems, they have many important applications, in particular in geophysics and radio locations and so on. And for us, it is important that very often they help to find very much simpler, much shorter solutions to spectral problems, because dynamical inverse problems and spectral problems are connected just by Fourier Laplace transform. And like engineers do very often, they switch from time domain to frequency domain and back when it's necessary. And I will demonstrate that the most simple algorithms for solving inverse problems come obtained by combining dynamical and spectral approaches. For example, Crane, when he obtained in 50s his famous method for solving inverse problems for recovering unknown density of a string. So he tried to use purely spectral methods, and the proofs was so complicated that not all details were proved until the works of the branch. But in 1971, Alexander Blagoveshchensky gave very simple proof of main Crane equations using dynamical methods. So Blagoveshchensky is a pioneer of dynamical, can be considered as pioneer of dynamical inverse problems. And in middle of 80s, we proposed the boundary control method for solving inverse problems, which is based on deep connections between controllability and identifiability. So the developing of classical idea of Rudolf Kalban, who in 60s did it. He used connection and proof some kind of equivalence between controllability, observability, and identifiability for linear finite dimensional systems. So we developed this idea for infinite dimensional systems. And certainly, I mentioned brief remark of Vyacheslav from his last talk that boundary control method is essentially the transformation method. Certainly, it is not true, because first of all, boundary control method was developed first of all for solving multi-dimensional and inverse problem for the wave equation. And when X is multi-dimensional then there are no transformation operators. So only maybe in some technique, in some illustration of boundary control method, I will do it in one-dimensional situation. For classical already solving inverse problems, there are some relations between transformation, but not technically, not ideologically. boundary control method is based or used or connected with transformation method. It is quite different ideas, quite different approach, quite different methods, and quite different goals. And for instance, even in one-dimensional situation, it is more close to Crane, not to Gelfand-Levitan methods, and Crane did not use transformation operator methods. Okay, so briefly I discuss, because I will use this for graphs. So what is the idea of the boundary control method on interval? We consider wave equation in this form with boundary control F, 0 in initial condition. And in this talk, I assume that Q is real, but it is not restriction. Non-self-adjoint version was proposed in the middle of 90s, so everything, it works well for complex potentials and for more general non-self-adjoint operators on graphs also. And we use this representation. Certainly this Bursa type representation reminds transformation, because in Gelfand-Levitan papers, this equation, this Bursa kernel also appears, but it is just, for us, it is just illustration of simple classical one-dimensional situation. And so we have this representation of solution. What is important is that for small t, which is less than L, this is well-known Bursa representation. For bigger L, there was no representation, but we can extend periodically the potential on the whole line from the interval, solve this Bursa problem 5, 6, and obtain this representation for all t. So for bigger t, we have bigger such terms. But what is important that after each new reflection from the end boundary, two such additional terms like main terms, integrals terms appear. So there are no exponential growth of these terms, and this representation, it is very useful for solving control and inverse problems on graphs, because on graphs we have many reflections from on different edges of the wave. Okay, and for inverse problem, our inverse data is a so-called response operator. It is just analog. It is dynamical Dirichlet-Neumann map. So it's Fourier Laplace transform gives us a value function. So it is important, but very well known, and is classical in inverse theory, not only interval, not only on graph, but for general linear inverse, linear in sense of our models are linear inverse problems. That response operator dynamical Dirichlet-Neumann map connected by Fourier Laplace transform with Weyl function or Weyl matrix function depending of our statement. And our inverse problem is to recover unknown potential on any interval. So capital T is less than L, less than length of the interval. So we need to recover potential using our dynamical operator. And because our response operator is completely determined by its kernel R, so it is the same like recover potential from this kernel are small. And so our approach is based on controllability. Controllability is essential part. So we introduce control operator, which maps our boundary control to solution at fixed moment of time. And controllability, it is proven invertibility of our control operator. So for any prescribed shape of the wave, we can find boundary control that the shape of our wave at the moment, fixed moment, capital T, is exactly as a shape that we prescribed. And in this simple one-dimensional situation, proving controllability is trivial because due to Boursa type representation, this invertibility of this control operator is equivalent to solvability of the Volterra second kind integral equation. And but controllability is an important part of boundary control method, and in all applications we need proof controllability. Here is simple, trivial even, but for instance, in multidimensional situation, it is extremely difficult, and it was controllability in this form was proved. It is uniqueness some. It is equivalent some kind of uniqueness theorem, and it was proved by Daniel Tataru only in the middle of 90s, later than boundary control method for multidimensional wave equation was created. So it is extremely proved because existence results of Hermander was not enough to prove a desired type of controllability. Even for graphs, I will show it later, this proof of controllability is pretty difficult, and it is approximately equivalent to by difficulties to solving inverse problem itself. But in this one-dimensional situation, we demonstrate this example to demonstrate main ideas of boundary control and to demonstrate how easily we can derive the classical Gelfand-Levitan or Crane equation just in several literally in several lines. So when we prove controllability, we introduce so-called connecting operator in this form, where adjoint to control operator is a very important observation operator. Observation operator maps boundary conditions. So we consider the same equation, but with zero boundary conditions, with some non-zero initial condition, and observation operator maps initial condition to the traces of our solution on the boundary. And I will return to this observation operator because it is more closely related to inverse problem. So, and then we consider a special control problem. So our control problem is to find the boundary control such that our solution, our profile of the wave exactly coincide with function y. A function y, it is a solution of Cauchy problem 7. And then using integration by parts, we derive equation, this equation, which is, it is Fredholm type equation, but is solvable because we proved that CT is invertible, but CT is invertible because our system is controllable and our control operator WT is invertible. That's all. If we solve this equation, we find solution special control FT, and using this solution and using propagation on singularity property against this Gursat type presentation, we by classical, it is rather crane method, we can find our unknown potential. And our equation, it is not crane equation exactly, precisely, not Gelfand-Levitan, but it's equivalent by simple algebraical manipulation. It can be reduced either to crane or to Gelfand-Levitan form equation. So it is absolutely equivalent. We can say the same equation. And again, I emphasize an operator, our response operator and value function connected with each other through the Laplace transform. And so if we know value function, we know response operator for all t, and vice versa. But if we, to solve inverse dynamical problem, it is enough to know a response operator on a final interval, on a time of controllability. And therefore, dynamical inverse problem a priori contain less information until we do not solve inverse problem. So the minimum possible information for solving inverse problem on interval or on compact tree, it is a response operator given on the controllability time. And in other words, we can say that it is a precise form of expression of so-called local Borg-Marchenko local Borg-Marchenko uniqueness results. So we recover to recover potential, we do not need the whole value function, but some asymptotic properties, some part of information. What part? It is exactly the statement that Fourier Laplace transform of a value function supported, not supported, it is enough to know the image of value function under Fourier transform on a finite interval, because it is exactly RT. So it is local Borg-Marchenko theorem, which can be formulated not only interval or half-line, but for graphs and other problems. Okay, and now I switch to control and inverse problems for trees. So it is well known that our control problem or inverse problem on tree is solvable if our observation are supported at all boundary versus but one of the boundary vertices. And generally, it is not solvable if our observation supported on a less number of boundary vertices, and I explain why. It will be clear in my later presentation of this solution. Okay, so now I formulate inverse problems on graphs. So on each edge, we have a standard Sturm-Liouville equation with with Dirichlet zero condition on boundary vertices and standard Kirchhoff-Neumann condition on internal vertices. So it is a continuity condition, and this is a Kirchhoff condition. So this capital E, it is a set of all edges incident to fixed vertex V, and derivative. This derivative means derivative along the edge EI. Taken at vertex V in the direction outward of vertex V, or inward, it does not matter, as we agree. And so two possible statements of inverse problems. So the first statement to recover first of all, our inverse problem, it is a recover not only potential that whole graph, it means that we recover topology, lengths of the edges, and potential, either from spectral data, it is a eigenvalues of traces of derivative of eigenfunctions on the boundary or on the part of the boundary. And another, it is a Weil matrix which consists of traces of Weil solutions, traces of derivatives of Weil solutions, again on the boundary and on the part of the boundary. And brief history, already Vyacheslav yesterday mentioned some of these works. So there are extensive list of references now about inverse problems on trees, and I will mention only some first problems in this direction. The all complete list of references can be found in these books. Berkalaika, Kuchment, Kurasov, and survey by Yurko. Belyshev in his paper used spectral data, eigenvalues, and traces of the derivative eigenfunctions, which are derivatives to the knowledge of the whole Weil matrix on the boundary, of the whole boundary, which used in paper of Brown and Weikert. Vyacheslav Yurko used just diagonal of Weil matrix, main diagonal, computed at all but one of the boundary vertices. In our paper with Pavel, we used Weil matrix, again computed at all but one of the boundary vertices, but Brown, Weikert, and Yurko assume that topology of graph and lengths are given and recovered only potential, while Belyshev and my paper to Kurasov, we recovered the whole graph, including topology. And we knew already, so the paper of Vyacheslav, certainly he definitely was the first who paid attention that the potential can be recovered only from the diagonal. And we mentioned this, we even demonstrated this in work with Kurasov, that we need the whole matrix where we need to recover topology, and below I describe how we do it. But if topology is given, then the potential and also the lengths of edges can be recovered only from the diagonal, like Vyacheslav did in his work. So in this case, but I can mention now answer in more detail to recent question of Vyacheslav was the difference of his methods and leaf peeling. Again, we use leaf peeling to recover the whole matrix potential. So we peel all the leaf and recalculate the whole matrix for smaller graph. And then we use leaf peeling. So this is the main difference. If we need to recover only potentials and edges, it is enough to use only diagonal, and we do not need to recalculate the whole matrix for smaller graph. It is not leaf peeling, rather leaf cleaning. Okay, and also in our paper with Pavel, we consider dynamical version and of inverse problems, but we combined dynamical and spectral approach. Pure dynamical version was considered in more later in these papers, and again, pure dynamical version is important, first of all, if we consider to solve numerically pure dynamical inverse problems. So we do not refer to some spectral method. And secondly, if we would like theoretically to prove the local Borg-Marchenko uniqueness result, so we do not need to know complete value for all spectral values of parameter of the Weyl function. Okay, and now about dynamical inverse problems on trees. So this is a formulation of dynamical problem. We consider this wave equation with boundary control on the part of boundary and fixed Dirichlet condition on another part of the boundary, and with standard continuity and Kirchhoff-Neumann equation. So our data is dynamical inverse operator, which defined here, and we prove that if controllable or observable part of the boundary contains all but one of the boundary vertices, and a response operator is known for sufficiently large t, and this large t is indicated directly, it depends on geometry, then our operator uniquely determines the graph. And so the idea of the leaf peeling method idea is very simple. So we define so-called sheaf. Sheaf it is a boundary star such that the only not boundary vertex is the only vertex. So we can have several boundary vertices and adjacent one internal vertex. Then using the response operator, we recover potential in the length here and here, then recalculate using Kirchhoff-Neumann, we recalculate condition and obtain efficiently our response operator corresponding to these vertices. But how we do it? Unfortunately, I have not space on this slide. I wrote this on here. So if we know just the only entry of response operator, and we apply this entry to scalar control function on this first boundary vertex, then it has this form. So if you know this local part of our big matrix operator, we have this term. So observing the response of the same vertex, we can recover this coefficient. So we can recover the degree of the first internal vertices and the length of first edges. So observing this main terms, two singular terms of response operator, we can recover length, degree of the first internal incident internal vertices, and this part is responsible for potential. If we know this response operator, we know this kernel, and like in one dimension, using this small r, we can recover potential on the first edge. This is the idea. We use locality, the fact that our dynamical data is local. So this part of the response operator independent on all other part of the graph. So these three dots, they include all other information which connected to all other part of the graph. But this is related to the first edge. And certainly, Vyacheslav mentioned yesterday that he can do it in spectral form for corresponding entry M11 of function, because M11 it is just Fourier Laplace transform of this 11. Certainly, it can be this information can be extracted from corresponding spectral data. So here we obtain multiplication of K or IK spectral parameter. This is multiplication by AK multiplied by exponential, which take into account this shift, like after Fourier transform of the delayed term. So we can extract these coefficients, and this information contains information about. But it is much easier to extract this information in dynamical form than in spectral form. So there is advantages of disadvantages of both dynamical and spectral approach. So my claim is to extract information about potential lengths and degree of the first vertices of your edges. It is much easier to do in spectral form, but this recalculation of this data using Kirchhoff-Neumann condition from this shift to this stem edge, it is much easier to do it in spectral form, much easier numerically and analytically. And therefore, if we would like to have a more simple explanation of idea and more simple algorithm, we need to combine a spectral and dynamical approach. Okay, and to recover topology, we need the whole matrix, because if we know lengths of E1 and E2, L1 and L2, then we just put our control here and waiting for observation at this point. So we use R12 entry of our response operator. And we know edges, and we wait for signal. And if our signal, our wave appeared here at exactly at the moment of time which equal L1 plus L2, it means that these two edges are connected with each other through one common vertex. If, for instance, we apply control here and take observation here, not here, for instance, here, it is like this, we know this length. We understand that signal here appears only much much later. Signal goes here, here, and here. So we wait this time. We do not have see anything response here. We understand that these two vertices, these two vertices, 1 and 2, are connected through the common, these two through the common internal vertices, but this and this are not connected. And in such a type, such a we recover the whole topology. Okay, so I skip this because Vladislav already mentioned about our successful numerical experiments using leaf peeling and Bessel series. And now I briefly mentioned about controllability on tree because this ideas is useful for controllability and inverse problems for general graph. So how we use prove controllability on trees? So this is an example of tree. And here, when control X on all boundary vertices, here control X of all but one of the boundary vertices. And we prove that we can represent our tree as a union of disjoint paths, several black paths, one this path, this path, this path, this path. So several passes, and each path started from is a disjoint except of endpoints, and each path is controlled by boundary vertex. So we prove that every control every boundary control takes care about solving control problem of the corresponding path, and they do not interfere with each other. And in this type, we prove controllability. Controllability is equivalent to observability. The observability is very close to solving inverse problem. And in our paper with my former PhD student, Yan Zhao, we obtain the shape type of controllability. So in this simple example, a tree with star tree with 3 edges and control supported at these edges, one on two. So if our control applied of 2 boundary vertices and the vertex 3 is fixed, then already after moment t equal 2, all domain filled by waves. So we produce wave here. So all graph filled by waves, but we do not able to prove controllability. To prove controllability, we need time 3, because this first control takes care about controllability on black path from here to here, and it does not care about what happens on a red edge. But control from here, it takes care about this red part, and altogether we can prove controllability in this sharp type interval. But as it claimed in previous papers, that optimal time of controllability is 4. 4 is the maximal distance from controlled boundary vertex to uncontrolled boundary vertex, and it is 4. But really sharp and optimal control time is 3. But when solving inverse problem, we need time 4, because we are not able to recover last edge 3 potential here until we completely recover potential here. For this, we need not even 3. For solving inverse problem, we need twice bigger time, 8. So we need time 6 to solving inverse problem here, time 2 to solving inverse problem here, and then 2 to solving here. To solve an inverse problem, we need time dynamical problem. We need time 8. Okay. Now I mention another version of inverse problem. So again, on 3, we have on 3, but instead of control observation of boundary vertices, we may consider in dynamical on spectral form. We have one control here, but observation on internal vertices. So we have one boundary control here. But what we measure, our observation, we have five observation. We make measure derivative here in this direction of this edge, and then here. So our red arrows, it is corresponding traces of the derivative of the solution corresponding to this boundary control. So we prove that we are able to solve our inverse problem using one control and this observation. So it is just row. So it is corresponding right column in Fourier transform for corresponding. We consider one Weyl solution. With one here and corresponding entries on value vector corresponding to this derivative. So this statement is totally physically relevant, because you can imagine that in applications, not all part of the boundary is accessible for observation or control. Then we need to support our control observation on a smaller number of boundary vertices, but we need to compensate this to solve inverse problems using internal observations. So we can combine here, it is just one control and several internal observations. So we do not need to take observation on the whole edges, because otherwise we just split our problem to several independent edges. So this is a minimal number of observations. We know about minimal number observation. We know that it is a number of boundary vertices, on the tree, number of boundary vertices minus 1. So you can see that using this another kind of observation, we need another the same number of the observation, 5. We have 6 boundary vertices, and 5 observation is enough to solve our inverse problem. And we can explain why. So now we switch to problems on the with cycles, but first we need to introduce Schrödinger operator, and multiplicity of spectrum depends on graph and on Q. If we change potential Q in some time and look for maximal possible multiplicity of eigenvalue. So maximum multiplicity of spectrum. So turned out that this number depends only on graph. It is independent on lengths of edges, and it is important characteristics. And it is graph invariant, and it was obtained in a nice paper of Katz and Pivovarchik. So what exactly they obtained? If we have a cyclically connected graph without boundary, This number sigma multiplicity is mu plus 1, when mu is a number of independent cycles, cyclomatic number. If we have a 3, it is gamma modulus gamma minus 1. If we have a quasi-3 like this, quasi-3, if any cycle have at least two connected points with other part, we have gamma minus 1 plus number of cycles. And there is a formula for in general situation. Okay, and so we can prove that if we have less number of control observations than this characteristic sigma, that our system is not exactly controllable and observable, and therefore it is typically not identifiable because through boundary control, observability and identifiability are directly connected with each other. Okay, and how we solve inverse problems on graph with cycles? First of all, I mentioned there are, as I know, there are inverse problems. So several papers by Vyacheslav Yurko and several papers by Pavel Kurasov about, and our approach is quite different. What is the difference? So Vyacheslav used several spectra to solve inverse problem. The one main spectra in this, say, spectra of the whole system, and another spectrum or spectra, it is a spectrum of a part of the system, like spectrum of this edge with say Dirichlet boundary conditions on the edges. So it is kind of destructive results. So we use information not about whole system, but about some parts of the system. So it is a legitimate statement of inverse problems and with probably important application, but it's another statement. We try to solve inverse problems through information only about the whole system. Not about separate part of the system. Pavel Kurasov, he used magnetic Schrödinger equation, used some information of magnetic flux through the contour of the graphs additionally, and his definition of corresponding while function or while vector are quite different. So it is quite different approaches, quite different statement of inverse problems and different results. And as I know, neither Vyacheslav nor Pavel claim they solve inverse problems on general graphs without any additional conditions of restriction. So we try to solve problems of any compact graph with cycles. For example, for this picture, we use, like in previous tree, we use one Weyl solution. So it is we put one here, and we use two observations. One derivative in this H1, so it is derivative of first vertices along the first edges, and another derivative of the second edges on the second vertices. And we prove, like on trees, we prove solvability, and with Vladislav Kravchenko we even started to discuss numerical realization of this approach. Why two? Again, because according to Katz-Pivovarchik formula, either we have just a ring without edges, or a lasso, a ring with an wedge. edge, or ring with two adjust edges. In any these three situation, maximum spectra is 2. And therefore, we hope and we really prove that 2 observations are enough to prove observability and to prove solvability of an inverse problem. Okay, and now, okay, so this is a statement of observation. So what we can observe? So at each edges, internal edges, we have Kirchhoff-Neumann condition. So we can observe either derivative of any sort, either or function phi. On boundary vertices, function is fixed. We can observe only derivative. So we potentially we can put arbitrary many observations, but we need to find the minimal possible, and minimal possible it is sigma. But in many cases, we can solve control and inverse problem with such kind of sigma, and in some cases, we need bigger. So what we do? If we have arbitrary graph with cycle, we start first with acyclic orientation. There are many possible acyclic orientations, so you can numerate some arbitrary numerate vertices. So here we have 13 vertices, and then we direct arrows from bigger to smaller, like waterfall, and you obtain acyclically direct graph. So if we have a loop, you introduce artificial edge to get a cyclic orientation, edge of degree 2. So we allow multiple edges between two vertices. We allow loops. We start with acyclic orientation, and after that we put observations. So if we put observations, so the question is to put minimal number possible, but big enough to solve inverse problem. So again, we observe that on this picture we have two sources. So 13, 12, 10, 8. So it is sources, so no incoming, only outgoing vertices. And two sinks, no outgoing, only incoming vertices. Okay, so what we do? On internal sources, we put observation functions and derivatives. On boundary sources, we take only derivatives. So, and we put derivatives number of outgoing vertices minus 1. So here is 2. Here is 2. Here we have 3 outgoing, 1 incoming. So we have put 2 and so on. Okay, and then the center part, we are able to prove that like for trees, we can split this graph for finite number of disjoint passes, and each pass is started from active, so-called active vertex or active edges. So roughly speaking, each individual pass is absorbed or controlled by corresponding active edge or active vertices. Okay, okay, we can see that minimum number of controllers corresponding to the previous picture is a number of controllers needed for this spanning tree plus numbers of cycles. Spanning tree, it is a tree which obtained from the graph by removing minimal number of vertices which contains cycles. Okay, but how to obtain minimal number of controllers as a graph invariant, like sigma? So we can split in previous graph, we can split on so-called blocks. And if we, but by cutting this graph at some vertices to obtain component, separate component of the graph, and count the number of boundary blocks. And we obtain these characteristics that number of observers, minimum possible number of observers can be obtained in this way. So if we have one block, again, and if we have more blocks, this formula. So like for sigma, we obtain this kappa dependent only on topology of graph, like its graph is invariant. So it is already independent of orientation. So any specific solution depends on orientation, but this characteristic independent of orientation, and this is a graph invariant. And what we can prove that for all graph, we say this characteristic, it is expected result. So we cannot hope to observability, controllability, or identifiability if our number of observation less than number of possible number of spectrum. Fortunately, for many cases, for trees, quasi-trees, rings, lasso, they coincide. So we cannot do better. But unfortunately, for other graphs like flowers, Shabamile flowers, we have many connected cycles and each independent components. We may have that this kappa became much bigger, which number of cycles bigger and bigger. So what we can guarantee? So if we have kappa or more observers, we can guarantee exact controllability, exact observability, and stable identifiability. So we have an algorithm solving inverse problem like leaf peeling for trees, because we can split present our graph in union of independent disjoint passes, and if we have a number of controllers, observers, which less than sigma, then generally we do not have even approximate controllability, and generally we do not have uniqueness, even uniqueness property in observation and identification. Between kappa and sigma, we may have uniqueness, but my conjecture that we do not generally have stable identification. So if we may prove uniqueness in some situations. There are examples of uniqueness of controllability, observability. But if we perturb a little bit potentials or lengths of edges, we immediately destroy this observability or identifiability. Thank you very much for your attention.
Well, thank you, Sergei, for this very nice talk. Are there any questions?
See, I have several remarks, if it's possible.
Sure.
You see, of course, I agree with Sergei that the dynamical approach is a very good approach for many problems, and especially for multidimensional problems. But I'm not specialist in multidimensional case, and I'm sure that this approach can be used for multidimensional case. But let's confine ourselves only one-dimensional case. Namely, this case was considered in my talk and then Sergei's talk too. So my first remark is that for one-dimensional case, boundary control method is the modification of the transformation operator method. Here I don't agree with Sergei. The second remark, that for one-dimensional case, if we studied problems on graphs, this boundary control approach is weaker than approach by combination of the method of spectral mappings and the pseudo-cutting procedure. My third remarks about the leaf peeling method. It's really my method. It doesn't make, of course, my ideas, pseudo-cutting procedure is used for a little bit another situation. They recover a little bit different data, but the same ideas, the same method. So it's not new method. It seems to me that it doesn't make sense to give another name for the well-known method. And the next remark related to the inverse problem 1. As I remember, it's the slide 14. You see, I agree that in order to reconstruct the potential on the tree, it's sufficient to specify only a part of the diagonal. It's my statement. But now let's consider another inverse problem. We would like to reconstruct not only potential, but also the structural graph. It's a little bit different problem. And the statement of inverse problem 1 is we need to specify the whole matrix. But you see, it's a huge overdetermined problem. If we would like to reconstruct not only potential, but also the structure, it, roughly speaking, we need to reconstruct additional several numbers. Let's say 20 numbers. And in order to reconstruct 20 numbers, we specify huge information, a lot of analytic functions, the whole matrix. Of course, it's not an adequate statement. It's necessary to find a new statement where additionally to the part of the diagonal matrix, we have to specify additionally maybe some other 20 numbers from the spectral characteristics, maybe 20 eigenvalues or something else. Otherwise, it will be a very overdetermined situation. And my last remark related to problems on graphs. Here, I don't agree with Sergei that in my papers, I solved the problem for arbitrary complex graph. Arbitrary, it was many years ago. And in this case, my statement is specify some spectra, but the spectra related not to part graph, but the whole graph. Only some of the spectra is measuring using the measure not only for boundary vertices, but for some interior vertices. It's more or less natural for in applications and so on. So the statement, all spectral data related to the whole graph, but not for the part of them. And only I repeat, it doesn't make sense to repeat. And on the contrary, in the Sergei's approach, on the contrary, the controllability related to part of the graph, part of the weight. So this situation is quite different. So it's all my remarks. Thank you very much.
Okay, I'll try to answer all questions, but it was, I believe, several, maybe 8 or something questions, because, and therefore I'm not sure that you can may remind me if I miss something. First of all, first remark. So you insist that boundary control in one-dimensional situation is essentially transformation. So I disagree this again because again I repeat, it is for instance Crane, he did not use transformation method, and our method is much closer to Crane's than to Gelfand-Levitan. So I do not see any any basement for this statement that it is boundary control in 1D is the same that even for interval, even for semi-axis. Moreover, on graphs, on graph, for instance, on trees, we use boundary control at very beginning, only at one point to recover potential lengths of this individual boundary vertex and degree of this vertex V1. Only this we use boundary control. Then then it is leaf peeling. It is not boundary control. It is leaf peeling. Okay, now it's about terminology. I agree that I repeat once again that Vyacheslav was the first who noticed very important fact that to recover potential we can use only diagonal of Weyl matrix, or in my dynamical statement, diagonal of response operator. It is absolutely true. But I repeat that we developed leaf peeling, proposed leaf peeling to recalculating the whole metric. So we cut these three edges, we obtained new graph, and we are able to recalculate all entries of new response matrix operator on new matrix Weyl function through the origin. I absolutely agree that we do not need this. It is absolutely not necessarily necessary information to solve even general, even recurrent topology. We do not need to recalculate on each step this step. It is just independent fact. Leaf peeling, we can recalculate on each step, obtain completely new inverse matrix. And again, what's the difference between Vyacheslav method? His method, it is not leaf peeling, it is leaf cleaning, I would say. We recover potential here, and it goes further inside of the graph. We do not cut. At each step, we use original Weyl solution, which defined through the original graph with data 1 on original boundary vertices. And this solution enough to recover potential. I absolutely agree. And I agree that we do not need the whole matrix to recover even topology. But we can do it for any specific graph. We can say exactly how much information we need to recover, how we need additional entries we need. So roughly speaking, we need these non-diagonal elements to recover connectivity of this sheaf. Okay, so certainly I agree. And how many non-additional elements we need, it depends. So just we formulate just general statement. If we a priori use the whole response matrix or Weyl matrix, we can recover topology of arbitrary tree. Okay, this is first set of questions. About graph with cycles. Again, my understanding that for instance, you use something from this something graph spectrum related to this part of the graph. So
No.
What this?
All spectra are related to the whole graph, not the part. It's not true.
Okay. What spectra you use additionally to spectra of the whole this graph? Because on this example.
I don't remember how many spectrums, but all spectrums in each graph, not only this simple one. we need the different boundary conditions. If we a little bit consider different boundary conditions, we get another boundary value problem, but for the whole graph, not for the path. We change boundary conditions and get another spectrum.
Okay, so
But I don't remember exactly which spectra, but really the situation is.
I will not dispute you know your papers better. So certainly, my impression was that part of your information spectral related to not whole graph but to some part of the graph. Okay, it is. Maybe true, but I do not understand your last remark that for controllability I use information related to part of the graph. It is not true. What is this? What do you mean?
But maybe it's my mistake. Maybe I did not understand exactly. But when you have some pictures, you choose some way which you have a controllability. As this way corresponds to the part of the graph. Maybe it's my mistake.
I use what? Some?
In the picture, I did not understand exactly formulas, but in the picture, you show that some.
What picture? What picture is this or?
No, next one. Here. So you use some way, but not for the whole graph, but for some way.
No. This is not picture about graph. This is my graph. This picture just illustrate how I can very fast calculate the possible number of controls. So it is a spanning graph. My graph is this. I use control, or more exactly, I use observation. Putting what here. So all my observations are marked as red. So it is one system, not part of it's one whole system with prescribed boundary and boundary conditions. And I use only this observation. And all our control observation and inverse data are constructed from this observation related to the whole graph.
Okay. Maybe it was my mistake. But it's different statement of course.
Yes, absolutely. Yeah, I claim this. Yes, it is absolutely different statement, different inverse problem. So did I answer your questions, Vyacheslav?
Okay, in some questions I agree with you, in some question I again not agree, but maybe it's enough for discussion.
Okay, thank you.
Thank you.
Well, I think Pavel wishes to ask a question. Pavel?
Hello.
Yes, you wanted to ask a question, right?
Yes, if somebody else can also ask. Sergei, two short non-expert questions. Do I understand properly that for your dynamical method, it's vital that you use wave equation on the graph, which is non-dispersive, so to say the classical dynamics on a quantum graph?
Yeah, yes. I use this. So this equation related to Schrödinger equation, Schrödinger operator, just for Fourier Laplace transform. It is if you are interested only in Schrödinger operator, you may consider this so-called wave equation like artificial object. You make a Fourier Laplace transform from the Schrödinger operator, and you obtain this object. That's
exactly.
That's all.
And my second question, when people try to reconstruct the topology of the graph from spectral data, often it is needed that the edges are incommensurate. There is a do I understand properly that with your dynamical method you do not need such an assumption?
Excuse me, what additional assumption? Repeat, please.
The assumption that the edges are incommensurate, that they are
Oh,
irrational.
no. In my approach, no. I would. It is very important for my approach. I would like to obtain results, stable observability and stable and identifiability result, which absolutely independent of such non-physical parameters. So my results are stable with respect to perturbation of lengths. But if we have potentials, it does not make sense to talk about commerciability of the lengths, because this relates only to trivial potential. Certainly, I agree. Some kind of very interesting results which relate to trivial potential, to Laplace operator on graphs, they depend heavily on rational and irrational rationality ratio of lengths. Yes, I agree that then for recovering topology of such a graph, we need much less information if we have a rational independent lengths. But it is quite different kind of inverse problems. I consider for Schrödinger operators, so I would recover to obtain stable stable result for solving inverse problem recovery Q, and therefore all my results are stable and independent of such characteristics like rationality. It is another kind of results that are interesting and important, but not related to recovering unknown potential.
Okay, thank you.
Is there any other question? Well, if not, we thank Sergei for his very nice and illuminating talk.
Thank you.
very much.
Thank you. Well, then, for those who did not join earlier, I remind all of you that you can listen to the talks in the YouTube and Facebook channels of EMAS. And then if there are no further comments, we should meet tomorrow at 9 Mexico City time, right?
Okay,
If there are
bye-bye.
no more questions or points, then I will close the session. Okay, so see you tomorrow.
See you tomorrow. Thank you very much.
See
See
you.
you tomorrow.